MPLS Layer 3 VPNs. Now, just like I did with the MPLS VPN infrastructure, I'm going to explain these from a theoretical perspective, and I'm going to explain how the data plane works and how the control plane works, and then we are actually going to go ahead and implement that. So, to take a look at how the control plane in MPLS works, let's build a very, very simple MPLS network. So what I'm going to have here is I'm going to have some sort of a cloud. So there is some MPLS that runs here. And I'm going to have two customers. I'm going to have customer 1, site 1. And I'm going to have customer 1, site 2. So let's say that they are connected here. And I'm going to have customer 2, site 1. And I'm going to have customer 2, site 2. Now, let's say that these are connected to the same MPLS node, to the same device on two ends of my MPLS cloud. Now, in MPLS terminology, these devices are called provider edge routers. So this is going to be PE1 and this is going to be PE2. Now, keep in mind that I mentioned before that in MPLS terminology, these devices that sit at the edge of the MPLS network are called edge label switching routers. Technically speaking, provider edge nodes are still edge LSRs, but when we are talking about the terminology used for MPLS VPNs, these are provider edge nodes. And these devices here, they're called C11, C12, C21, and C22. These are actually customer edge devices, the CEs. So this is a CE and this is a CE. Now, the routers that might be sitting inside this cloud here are called the P routers, or the provider routers, and the routers that might be sitting behind these customer edge routers are something that we call C routers, or the customer routers. But these are, at this point of my story, relatively irrelevant. So this is what I'm going to have, and on top of this, this is going to be the addressing scheme used in these customer sites. So customer 1.1 will be using in their site 192.168.10/24. So this is the network used by customer 1, and this is going to be the network that is going to be, let me just write it down a little bit nicer because I will be needing it a couple more times. So 192.168.10/24. So this is the network used by this customer here, and this is going to be the network that is in use by this customer here. Now, on this side here, I will be using 192.168.20/24. And this customer here will be using the exact same address space. Now, this is going to present a unique problem for us as the ISP. Now, what is the problem going to be here? Well, we are using the same address space here and address space here. Now, being someone who has worked for ISPs all my life before I became an instructor, there is a perfectly valid solution for this problem that ISP can give you. You as a customer, please renumber your network. Now, sometimes you are ISP who has a really, really big and important customer, and this is something that you cannot really do or tell customers. And I can tell you from experience that even if it's not a really big and important customer, customers really don't like hearing that particular answer. Even though from perspective of the ISP, this is probably the easiest solution for this problem. So, let's say that this is not an option, that the customers are unwilling to renumber, but nevertheless, we somehow need to provide the communication from the one blue site to another blue site here without actually providing for the crosstalk between these sites. So how can we do that? Well, this involves several steps. Now, one step is that we need to provide a separation of routing domains. We need to find a way to separate this blue routing domain here from this red routing domain here. So we need to find a way to separate these two. Also, on this side here. So we need this blue routing domain here, and we need this red routing domain here to be separated from each other. Now, this creates 3 routing domains. I'm going to have the black routing domain. I'm going to have the blue domain. And I'm going to have the red domain. Okay? So the black routing domain is what we call the main routing table here. The blue will be used for customer 1 and their 2 sites, and the red one will be used for customer 2 and their 2 sites. So let's see how that works. So for the separation of these routing domains, we can use feature that we call VRF. Now, some people call it VRF. I personally like to pronounce it as VRF. I don't know why, but VRF for some reason always hurts my ears. Now, what this stands for is the VPN routing and forwarding. And what it basically is a separate routing table and a separate forwarding table that will be used for these separate routing domains. So basically what we are creating here on top of already one, and the main routing table could conceivably be called a VRF as well, or the global VRF, the global routing table. So we are going to create a copy of the routing table, another instance of routing table, not a copy, because copy implies that some data from the black routing table will be copied into blue, which is not necessarily true. I should say it's not true by default. You can get some data from one routing table into another, but by default that does not happen. So what we are creating is another instance of routing table here, another instance of routing table here, and which is the same thing that we are going to be doing on PE2. We are creating a blue instance and we are creating a red instance. Now, but this also stands for forwarding table. So there will be a subset of Ceph that is created that is going to be used for this domain, subset of Ceph that is going to be used for this domain, and subset of Ceph that will be used for this domain here. So we are going to have, technically speaking, one Ceph table that kind of has separate pieces, separate chunks, one that deals with the main routing table, one that deals with blue, one that deals with red. So this is going to take care of the fact that we have an overlapping address space on this one device here. But we have still not solved the problem. We are on a good way of actually solving the problem, but we have now provided for isolation on a single device. But that's not what we want. What we want to do is we want to get the traffic from one site to another in blue domain, and we want to get the traffic from one site into another site in the red domain. So what we need here is somehow that on this network here, that could be whatever, we don't really know how this network looks here. We somehow need to provide the ability to carry this blue or carry this red traffic across. Well, there is one solution, so this is not how it works. One solution would be to, on all of these devices here, to create the blue instance, create sub-interfaces in the blue routing domain, and also do the same thing for red. So create a red instance, add sub-interfaces, and send this traffic across like this. Oh, sorry. Now, if we had this situation, we are actually adding to our problem. What are we adding to our problem? Now, imagine that this was a relatively large or even medium-sized ISP, where you could have hundreds or thousands of customers. Now, I can tell you one story from my professional career. So before I became an instructor, I was working for ISPs, and at my previous work, that was in Iceland, so by any means not a large country, just 300,000 people living there. One of our PE devices actually had around 500 VRFs. So if we had that situation in Iceland, and we were by any measure not a large ISP, well, the largest in the country, probably the second largest I'd say, in the country, but by no measure large ISP, because in a country of 300,000 people, that's smaller than the town I live in right now. So can you imagine what in a decently sized country, a decently sized ISP will have in their network? So it's not entirely inconceivable to have hundreds or thousands or tens of thousands of customers and tens of thousands of VRFs in your network. Not necessarily on a single device, but in your network, yes. Now, if we added all these instances to the backbone of our network, we would have a network that is as stable as trying to balance on a feather, which is not going to be very stable at all. So what we need to do here is we need to find a way to get this traffic across without actually adding much complexity to the backplane of our network, to the backbone of our network. So do we have a technology for that? Now, if we only had a technology that would forward the traffic across this network based on information that is something other than the IP addresses, we actually do. It's MPLS. Because if we go back and look how MPLS works, when there is an actual label in place. So if we take a look at this table here. Now imagine that this packet arrives. So when this packet arrives here to R2, we are looking at the label 200 and then we are sending the traffic only based on that label. We don't care what the destination IP address was. So these routers R2 and R3 don't actually have to have routes to be. The only thing that they need to have is some way of actually getting this label installed. If we could get this traffic to R4 somehow, R4 could theoretically know what to do with this. And this is exactly what we can do here. So what we can do here is to get this traffic across our MPLS network. We can send the packet. So let's imagine what happens with the blue packet, for example. So let me draw a blue packet here. So this is a blue packet. Let me just change the color for it. So blue here domain sends the packet and it arrives to PE1. Now this packet is now going to get a label. This packet is now going to get a label here that we want to get this packet across to PE2. So this label goes in now. Now this packet is sent to this device here, the labels get swapped, 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 and eventually one node before R2, this label PE2 actually gets dropped. So what happens? The packet that arrives here to PE2 is no longer blue. This packet now is actually black. Let's see what happens with the red packet. Now the red packet is sent. When the red packet arrives here, it gets the label PE2, this gets swapped, 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 and the penultimate device here actually drops the last label and the packet arrives to PE2, but it arrives in a black routing table. So now PE2 needs to perform a lookup in a black routing table for, let's say, 192.168.2.15. If we don't have the route, this packet gets dropped. This packet also gets dropped. So one thing that we have done with MPLS, so MPLS alone can solve the problem of getting the traffic from PE1 to PE2. But now we have the problem of how do we sort the blue traffic into the blue domain and how do we sort the red traffic into the red domain. That's problem number one. That's the problem of the forwarding plane for MPLS VPNs. Another problem is how on earth did PE1 know that these destinations are behind PE2 and not behind some PE3 here, or PE4, or PE5? How did PE1 know this? So we have two problems here to solve. So problem number one. So problems to solve is our data plane, which means sort the traffic in appropriate forwarding instance. So I'm just going to underline forwarding here. And problem number 2 is control plane exchange routes between PE devices for different routing instances. And I'm going to underline routing here. So this is why we call them VRFs. VPN routing control plane and forwarding instances, the data plane. So we have 2 problems to solve, control plane and the data plane. Now, the data plane is relatively simple here. So I'm going to explain it after I have actually explained the control plane. So here I'm going to do the exact opposite to what I've done for the MPLS infrastructure. So I'm just going to delete this because I don't need all this stuff. I just actually need a little bit more space. So I'm here going to explain how the control plane works. So this is going to be control plane. How do we solve the control plane problem in this MPLS VPN scenario? In order to solve this control plane problem, what we need to have here is between our PE1 router and CE1, or the CE router that we call CE11 here, we need to have some way of learning routes. So let's say that problem is sorted. So this protocol that runs between the customer edge and the provider edge router, this is something that we call the PE-CE routing protocol. So between the PE and the CE, we are running the PE-CE routing protocol. Now, the supported protocols in the version of iOS that you will be running are the connected routes, obviously. You can use static routes. You can run RIP. You can run EIGRP. And you can run OSPF. Or you can run eBGP. Now, I mentioned earlier today that Cisco explicitly does not support configuring iBGP sessions on PE-CE sessions, but you can still do it. It will not give you any error messages, but you are going to have to do a couple of things manually in order to be able to make it work. So this is something that I find very unlikely that you will see in the exam. This is why I explicitly wrote here that we are supporting, or that Cisco supports eBGP and not iBGP. So these are the possible PE-CE routing protocols, and for the exam, you should know how to use all of them in order to get this working. So let's say that bit is sorted so that we do actually have a PE-CE routing protocol in place, so that somehow in the blue routing domain we have actually learned the routes, and in the red domain we have actually learned some routes. Now, when we have created these VRFs, when we have created these virtual instances, we have created VRFs using the VRF creation syntax in iOS, and there are actually 2 ways of doing that. There is an old way and there is a new way of doing it. So when we create the VRF, there are 2 ways of doing it. Old, which is something that you will most likely be using, and the new, which some of you may have never seen. So the old way of creating it is IPVRF, then you specify the name, and then you specify some parameters here. Now, the new way of creating VRFs is using VRF definition, and then you specify the name. And here you can have some commands, and then you have address family, IPv4, and then you specify some parameters here. Now, the idea behind this new way of doing things is that you can actually use this new format to support IPv6 VRFs. So either one, you can use either one, but remember that if you are using the new format with the VRF definition, you actually need to pay attention for the address family IPv4 or address family IPv6, because without it, it's actually not going to be active in that address family. But if you are using old syntax here, this is for IPv4 only. Now, I find it very unlikely that you will need to do this for IPv6, but if by some chance they ask you to do that, this is the way to do it. So you have to use the new format for VRF creation. So let's say that here we have actually created some VRFs. So let's call it on this side, let's call it blue 1, let's call it here blue 2, let's call it here red 1, and let's call it here red 2. So when we have created these VRFs, we have created these separate routing and forwarding instances, and now we have the routes on the PE router. So let's say that we have this route learned on P1 and this route learned on P1, and they are in separate routing tables. So how do we actually get the routes from one PE to another? So for now, I'm just going to be interested in routes moving in this direction. So this is where I'm interested. So for data plane, the traffic needs to flow in the other direction. Now, mind you that we need the same thing, the same setup needs to happen in the opposite direction, but we are not going to explore just one direction of control plane so that we can look at what happens as the result in the data plane. So we have learned this route here, and we have learned this route on our P2. How do we get these routes across to P1? Well, we could run a separate copy of OSPF or a separate copy of EIGRP, whatever protocol we were running in blue or red domains, but then again, that would add the complexity on the backbone of our network. What we need is a protocol that can carry a large number of routes, an arbitrary number of routes, without actually being overwhelmed by the large number of routes. Now, what protocol could that be? Well, one protocol comes to mind, and that is, of course, BGP. So between PE1 and PE2, we could run, let me just do this. We could run BGP. So let's say now that in our BGP from PE1, from PE2 to PE1, we are advertising this route in the blue domain and this route here in the red domain. Now, if we take a look at these two routes, we can immediately tell that there is going to be a slight problem with this approach. Now, that slight problem is that these two routes are the same. Now, if BGP on P1 receives two routes that are the same, the BGP needs to go through the best path selection process. Now, it needs to choose which one of these two is the best. Now, the problem with that is that the blue one is the best for blue domain, and the red one is the best for the red domain. But BGP is still going to go through the weight, local preference, locally originated, AS path, origin, MED, whatever else comes next, and it is going to actually choose one of these routes to be the best. So if it chooses the blue one to be the best, that means that blue domain might be okay, but we are going to have the problem in the red domain. There is no other way that BGP can handle this situation. BGP doesn't support load balancing, BGP doesn't understand VRFs. BGP is actually just designed to carry routes in the IPv4 address family. But what if we didn't use BGP? What if we didn't use IPv4 routes? What if we instead sent something else? The routes that are not actually 32 bits long, but routes that are longer, that are, say, 96 bits long. This is why there is a concept when MPLS VPNs, when you are creating the VRF, when you are doing this stuff here, one of the things that you actually need to configure at this point is called the route distinguisher. Now, route distinguisher is a number, a 64-bit number, that you can specify inside the VRF that is going to be used inside BGP to make the routes unique. Now, this is the only thing that route distinguisher does. So let's say that on this side here, we have configured the route distinguisher, let's say 111. Let's say that on this side here, we have configured route distinguisher 112. Let's say that on this side, we have configured route distinguisher, which is 122. And here, route distinguisher 121. Now, I am using the convention in which route distinguisher is specified. So RD stands for route distinguisher. It's a 64-bit value, usually displayed as AS number and then some identifier, or IP address, then some identifier. Now, depending on which format here you use, you may have different ranges available for ID part. Now, I should also put this here with an asterisk, because you can't use all 64 bits, because there are other parts, other bits that are part of this route distinguisher, but still, this is the theory here. Now, another thing that is important, the only purpose of route distinguisher is to make routes unique in the BGP. I should say in multi-protocol BGP. This is the only thing that route distinguisher does. It is not used for any other purpose. Now, I should also point out it doesn't have to be the same in the sites that are part of the same VPN. So this is the case that we have right now. We can see that blue route distinguisher here is 111 and here it's 112. These sites are parts of the same VPN, but the route distinguisher doesn't match on them. This is perfectly legitimate. Now, mind you, it can match. It can be different, it can be the same. You can even have the situation that you have the route distinguisher the same here and here, and that would still work. Now, good luck troubleshooting that, but it would, as far as technology is concerned, this would be perfectly fine. Now, which values should you use for route distinguisher? Well, in real life, it's a matter of corporate policy. So it would be a decision that is going to be made by your team. This is going to be the policy that you're going to be using for route distinguishers. But in the lab, you are simply going to do either what the lab tells you or what you feel the most comfortable with. So you are usually going to have the instructions, configure this as the route distinguisher. Just keep in mind that, you cannot use the same route distinguisher on the same router for multiple VRFs. So this RD and this RD must be different. Everything else, there is really no rule for it. So let me make one more correction here on this picture, and that is that this is not BGP. This is actually multi-protocol BGP. So how is route distinguisher going to be used? Well, the way it's going to be used is we are going to take the route distinguisher here, and we are actually going to prepend it to the prefix. So this prefix, this route distinguisher here, which is 112, is going to get prepended to this prefix here, and then this route distinguisher here, which is 122, is going to be prepended to this prefix like this. So if we take a look at these two prefixes now, first of all, they are not IP addresses, they are VPN v4 addresses. So I should really say that this here are now VPN v4 addresses that are 96 bits long. Now, and another thing that we can see is that this address here, 112.192.168.20/24 and 122.192.168.20/24 are not the same. So now there is no best path selection process between these two because blue is different than red. So this solves us the problem of making the routes unique. This avoids the best path selection process on PE1. The route distinguisher here was used to make these routes unique in our BGP table. But as we can see, the route distinguisher on this side here and the route distinguisher on this side here don't match, which means that this doesn't actually help us in sorting the blue route into the blue domain and the red route into the red domain, the red routing domain. Now, I should point out that we could have used route distinguishers for this sorting purpose. Or I should say that the designers of this technology could have used the route distinguishers for this purpose, but they are not used for this purpose. Now, they're not used for this purpose for several reasons, but the major reason is that that would actually be limiting in which topologies we can actually implement using MPLS VPNs. We would be limited to, let's say, just full mesh or maybe hub and spoke, but we won't be able to use some of the advanced scenarios that are sometimes in the literature called the extranet or the central services VPNs, where we are importing just certain routes from certain sites, from certain central locations, but not actually providing any-to-any reachability in our MPLS VPNs. So in order to avoid this apparent limitation, the decision was not to use the route distinguishers to actually sort the routes in the routing domains. And this is the reason why I said that this is the only purpose that RD is used for. It is used to make the routes, let me just rewrite that because even I couldn't read it. It's used to make the routes unique. So this is the only purpose that RD is used for. So what is actually going to be used to sort the routes in the routing domains is going to be route targets. Now, route targets are communities or extended communities that are also configured as part of the VRF. So here we are going to configure a route target, and let's say that here we are going to use 100.102. And here we are going to use route target 100.101. And here we are going to use route target 100.202. And here we are going to use route target 100.201. Now, as we can see here, the route target here does not match the route distinguisher here. Also, the route target here does not match the route target here, nor the route distinguisher. Again, there is no requirement for this. You could use the same route target here and the same route target here. You could actually, and this is relatively common, use the same route target value as your route distinguisher, but there is no requirement to have that. And I'm actually going to write that. There is no relationship between RD and route targets. They are completely unrelated. The purpose of route distinguisher is to make routes unique, and the purpose of route target is to help the other side sort the routes in appropriate routing tables. How does that work? Well, on its own, the route targets don't actually do anything. Now, when we use the route target here, when we are configuring the VRF, no matter which actual option for configuring VRFs, and where is that syntax? There is that syntax. So no matter which actual syntax you are using to configure your VRFs, when you are configuring route targets, one of the things that you do here is that you are going to say route target export and then some value, and you are going to say route target import some value. Now, in this case, when you are using new definition, you have several options. One is you can specify route target. So I'm just quickly going to say route target. You can specify either here or you can specify here. Now, more specific wins. That means if you specified here and here, this setting here will actually override the one that applies to all address families. Now, that allows you to have one set of route targets used for, let's say, all address families, IPv4 and IPv6, and then it allows you here to add additional ones, right? Because you can have multiple these route target entries. You can have multiple route target imports or exports. So I shouldn't really say that more specific overrides the other one, but if you specify it here, it will actually apply only for this address family. But if you apply it here, it applies to all the address families. But no matter which method you are actually using in this case, it's important to know that you have this idea of export and import. Now, when you say route target, export, what you are doing and what are you doing when you say route target import? So what you are doing with this command is routes from VRF will have this route target attached when injected into BGP, or I should say multi-protocol BGP. What you are doing with the import, you are telling routes with this route target in BGP. So let me just correct that. With this route target in multi-protocol BGP, and I should say VPN v4 address family, will be installed in RIB of this VRF. So routes from this VRF, so this is maybe a word that is missing here. So routes from this VRF will have this route target attached when injected into MPBGP. And again, here I'm talking about the VPN v4 address family. So when we are exporting the routes, this is what it means. That means take the routes from this VRF, from this routing table, and when you are installing them into the MPBGP, attach this extended community, this route target. Now, on the receiving side, when we receive the routes in the multi-protocol BGP, the VRF is configured to look into those routes into the MPBGP and say, okay, I'm interested in this, and this route, but I don't care about the others. And this is done based on the route target. So route targets have the purpose to actually sort the routes in VRFs into the appropriate routing tables. So let me just go back to this. I'm going to create a copy of this page so that we can continue with it. So this export route here, so I should maybe modify my writing here, that this is the route target export, and this is the route target export here. So on the other side here, I should really import what the other side is exporting. So here I'm going to have route target import configured to import 102, that's the other side, and here I should configure the route target import 100, 101. In the red domain here, I will be importing whatever the other side is exporting, so this will be 201. And here, let me just move that a little bit if that is possible at this point. It looks like it is. So this side here is going to say route target import 100 202. So now, this thing here, what I'm importing here, and what I'm exporting here is actually what is going to bind these two VRFs. This is the connection that I'm going to have. Now, the route targets are carried on these routes. So on this route that goes from this side to this side, I'm going to have the route target of 100, 102, and on this side here, I'm going to have route target is 100, 202. So now at this point, I have actually solved a major problem that I had. This is the control plane. This is how the routes are going to end up in the routing table here, how they're going to be sent to the other side, and how they're actually going to be sorted into appropriate routing table. Let's now send the traffic. So now the data plane problem begins. So if we take a look at the data plane, for data plane, I actually care about this in the exact opposite direction. So this is what I care about now. So this is now data plane. So as the result of this route making it here, C1 is now going to send some traffic. So it sends that blue packet. And this blue packet arrives here. Now, we are going to attach that label that takes it to PE2. So that label, let's just call it PE2 label. So this label here is now attached. So what's going to happen is this is going to be popped, swapped, and whatever happens with this label across. And finally, there is going to be penultimate hop popping, which is going to drop this label, and the blue packet arrives here. But the blue packet in the main routing table means black, right? So it gets dropped. So we are back to square one. I have solved the control plane, but I have not solved the data plane problem. Why? Because the packets don't have different colors. They're all the same. So I have solved the problem of getting the traffic across from P1 to P2. But this label here was used, or these are different labels that are used here hop by hop, just like we did in our MPLS infrastructure. These are the LDP assigned labels. So these labels here are helping me get the traffic from P1 over to P2, but they don't help me sort the traffic into appropriate forwarding instances. What I need here is something to help P2 identify that this is actually a blue or red traffic. What I need is some label that PE1 is going to install on the packet based on the information that PE2 told it. And this is exactly what's going to happen. So what's going to happen here is that in addition to route distinguisher and route target, there is going to be an actual label. And let's say that in this case, it's going to be 1001. And in this case, let's say it's going to be, let's say that this is 1002, sorry. That this is going to be 1001. Let's say that on this side here, we are going to be using label, let's say 2001, or 2002, sorry. And on this side here, let's say that we want to use label 2001. So this label is actually going to be communicated in BGP. Of course, I'm getting everything wrong now, so let me correct that. So this is going to be label 1002, and this here is going to be label 2002. So now what's going to happen is when this packet, this blue packet, arrives from C11 to P1, before sending it across, what P1 is going to do, it's actually going to install the label on this packet here, telling it that this is actually blue packet. So it's going to install this label 1002. So it's going to put it here on the packet, and then it's going to use the LDP assigned label to tell these routers on the network here that this needs to go to PE2. Now remember what swap operations do. They always operate on the topmost label. So this is going to be swapped, 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 and at the penultimate hop here, this is going to be popped because this is a topmost label. But the blue label gets intact, which means that the packet that arrives to PE2 now actually has one label. And this is the blue label telling PE2 that this packet actually needs to go into blue domain. We are going to have the same thing for the red domain. Now, these two labels actually have their names. This label here, PE2, is something that we call transport label. This label here is something that we call VPN label. Now, there are two things about the VPN label that are maybe not important but interesting to know. Number one is here I have shown you the label as sent in a BGP attribute, in a BGP update as a separate attribute. Technically speaking, label value is part of the RD. Technically speaking. Now, why do I say technically speaking? I'm saying that if you were to do Wireshark packet captures, this is where you will see which label was actually sent. But if you are running debugs in iOS, iOS is actually going to show the label as if it was another attribute. So what is actually happening on the wire might be a little bit less relevant for you when you are troubleshooting MPLS VPNs, because it's more important what iOS is telling you. So technically speaking, RD field, RD part of the VPN v4 update is where the label is going to get encoded. But when you are actually troubleshooting, when you are running debugs, like for example debug IP BGP VPN v4 updates, when you get the update, it will be shown as a separate attribute. That's one thing. The second thing is that iOS by default is not going to do what I've done here. It's not going to assign one label for the whole VRF. It is actually going to assign one label for each route in the VRF. Now, that has some advantages. That has advantages that when this packet actually arrives here on PE2, based on this blue label here, if this actually told us that this is the network where we need to send, we could actually encode in our Ceph exit interface, the next hop, and the layer 2 encoding. So just based on the blue label, we can actually send the traffic where it needs to go. If this was simply identified the routing table in which to send this packet to, or sorry, the forwarding table where to send this packet, we would actually have to perform an IP lookup. So we would know in which table to perform the lookup, but we would need to still do the lookup. So you hear there is kind of a balance between, do you care more about the memory? Because if you have a large number of routes in that VRF, like for example a full internet table, don't do that. If you have a full internet table inside VRF, you are going to have incredibly large number of labels, incredibly high memory consumption. But when it comes to the forwarding efficiency, this would be tremendously faster because every single packet that arrives, you know exactly where to send it. Now, if you are more concerned about the memory and not so much about the throughput performance, which, you know, depending on which hardware you use, could be the case that, you know, the memory is a problem. If this is the case in very, very new versions of iOS, you can actually tell it to assign the label per VRF and not per route. But this is not the case in the iOS version that you will have in the lab. So the reason why I'm telling you this is that to know that this is relatively simplified overview of how this works, because I wasn't talking about per route here. I was talking about, oh, this is the label that gets assigned for this VRF and so on. But you should know that in the actual iOS, what's going to happen is you are going to have one label for each VPN route. One question that I have here is, so we now know that this label here that gets assigned is going to be assigned per route. But what about the transport label? What about this PE2? Is it going to be the same for all destinations? The answer is yes. It will be actual peering endpoint of this router. So if they were peering between the loopbacks here, this BGP peering was between the loopbacks, the actual label that is going to be used as the transport label will be the same label that is used to send traffic to this loopback. So no matter how many routes we actually have in the VRF here, we are always going to be using the same transport label. It will only be the VPN label that is different, because remember, the VPN label is the only one that is end-to-end. The PE label is the one that is exchanged between different nodes here. And these nodes here probably have no idea about any routes from here. So PE label, the transport label, is always going to be the same, and it will be the peering endpoint of this device here.